The 125% demand factor is a concept used in electrical calculations, specifically when determining the appropriate size of conductors for electrical circuits and feeders. It's crucial to understand that the application of this factor differs between phase conductors and the neutral conductor. The code does not require that the neutral conductor be sized based on the 125% demand factor. This factor is primarily applied to the phase conductors to account for continuous loading. Continuous load is defined as a load where the maximum current is expected to continue for 3 IOs or more. In situations involving continuous loads, the overcurrent protection device and the conductor itself must be rated for 125% of the continuous load. For example, if a circuit has a continuous load of 20 amps, the overcurrent protection device should be rated for at least 25 amps, 20 amps x 1.25, and the conductor should be able to carry at least 25 amps continuously. The neutral conductor, on the other hand, is typically sized based on the actual calculated load it is expected to carry. This load is determined by the unbalanced current between the phases in a three-phase system, or the current returned to the source in a single-phase system. The neutral conductor's primary function is to carry the imbalance of current between the energized conductors. This imbalance occurs when the loads connected to each phase are not equal. Therefore, the size of the neutral conductor is directly related to the magnitude of this unbalanced current. Consider a scenario where you have a three-phase system with the following loads. Phase A has a load of 30 amps, Phase B has a load of 40 amps, and Phase C has a load of 50 amps. In this case, the neutral conductor would need to carry the unbalanced current. The maximum unbalanced current can be estimated by subtracting the smallest phase current from the sum of the other two phase currents, although more complex calculations may be needed for precise determination. In this example, the neutral current would be some value less than or equal to the maximum difference. Therefore, the neutral conductor would be sized to handle this calculated unbalanced current without applying the 125% demand factor. The reason for this difference in treatment between phase and neutral conductors lies in their respective roles. Phase conductors are responsible for carrying the entire load current to the equipment or devices they supply. Because of the continuous load requirement, they must be sized to handle the increased current demand. The neutral conductor, in contrast, only carries the unbalanced portion of the current. The NEC provides guidelines and tables, such as those found in Article 220 in Chapter 3, for calculating feeder and service loads, and for selecting appropriate conductor sizes. These tables and guidelines help ensure that electrical systems are designed and installed safely and efficiently. Some resources might present simplified methods for sizing neutral conductors, as these methods are not explicitly mandated by the NEC. While such methods may offer a general rule of thumb, it's essential to understand the underlying principles and code requirements. Always refer to the latest edition of the NEC and consult with qualified electrical professionals to ensure compliance and safety. In summary, the 125% demand factor is applied to phase conductors to account for continuous loads, whereas the neutral conductor is typically sized based on the calculated imbalanced load it is expected to carry. Understanding this distinction is crucial for accurate and safe electrical system design. When dealing with electrical calculations in conductor sizing, it's always recommended to consult the latest edition of the National Electrical Code and seek guidance from qualified electrical professionals. This will help ensure that your electrical systems are safe, efficient, and compliant with all applicable regulations. Now let's discuss some specific scenarios where neutral conductor sizing can be particularly important. Firstly, consider multi-wire branch circuits. These circuits share a common neutral conductor between two or more ungrounded conductors. In such cases, the neutral conductor carries only the unbalanced load from the ungrounded conductors. If the loads are balanced, the neutral conductor carries very little or no current. However, if the loads are significantly unbalanced, the neutral conductor can carry a substantial amount of current. Therefore, it is crucial to accurately calculate the unbalanced load and size the neutral conductor accordingly. Secondly, dwelling units present unique considerations for neutral conductor sizing. The NEC provides specific rules for calculating the neutral load in dwelling units, taking into account factors such as the diversity of loads and the potential for imbalance conditions. These rules are designed to ensure that the neutral conductor is adequately sized to handle the expected load. Thirdly, in commercial buildings, neutral conductor sizing can be more complex due to the variety of loads and the potential for significant imbalances between phases. For example, lighting loads, receptacle circuits, and 8-track equipment can all contribute to the overall neutral load. Careful consideration must be given to the types of loads, their operating characteristics, and the potential for imbalance conditions when sizing the neutral conductor in commercial buildings. Furthermore, the presence of harmonic currents can significantly impact neutral conductor sizing. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. These harmonic currents can add up in the neutral conductor, even if the fundamental frequency currents are balanced. In some cases, the harmonic currents can exceed the fundamental frequency current, requiring the neutral conductor to be significantly oversized to prevent overheating. The NEC provides guidance on dealing with harmonic currents in neutral conductors, including requirements for using larger conductors or directing conductor ampacities. It's essential to consider the potential for harmonic currents when sizing neutral conductors in buildings with significant electronic loads. Now let's delve further into the practical implications of correctly sizing the neutral conductor. An undersized neutral conductor can lead to several problems, including voltage drop, overheating, and even fire hazards. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source end. This can cause equipment to malfunction or operate inefficiently. Overheating can occur when the neutral conductor is carrying more current than it is rated for. This can damage the insulation of the conductor and potentially lead to a fire. An oversized neutral conductor, on the other hand, is generally not a safety concern, but it can increase the cost of the electrical installation. Therefore, it's important to strike a balance between safety and cost when sizing the neutral conductor. To ensure accurate neutral conductor sizing, it's essential to follow a systematic approach. Firstly, gather all relevant information about the electrical system, including the types of loads, their operating characteristics, and the potential for imbalance conditions. Secondly, calculate the expected neutral load using the appropriate methods outlined in the NEC. Thirdly, select a neutral conductor size that is adequate to handle the calculated load, taking into account factors such as ampacity, voltage drop, and the presence of harmonic currents. Fourthly, verify the conductor size using appropriate calculations and tables in the NEC. Finally, document all calculations and decisions for future reference. In addition to the NEC, other standards and guidelines may provide useful information on neutral conductor sizing. These include standards from organizations such as the Institute of Electrical and Electronics Engineers and the National Electrical Manufacturers Association. Consulting these resources can provide additional insights and best practices for neutral conductor sizing. In conclusion, neutral conductor sizing is a critical aspect of electrical system design that requires careful consideration of various factors, including load characteristics, unbalanced conditions, harmonic currents, and applicable codes and standards. By following a systematic approach and consulting relevant resources, electrical professionals can ensure that neutral conductors are sized correctly, resulting in safe, efficient, and reliable electrical systems. Always remember to consult the latest edition of the NEC and seek guidance from qualified electrical professionals when dealing with electrical calculations and conductor sizing. This will help ensure compliance and safety. It is crucial to have a thorough understanding of the principles and requirements related to neutral conductor sizing to avoid potential problems and ensure the safe and efficient operation of electrical systems. Remember that the 125% factor applies to phase conductors under continuous load conditions, while the neutral conductor is sized based on the maximum unbalanced current it is expected to carry. Consulting the NEC and seeking expert advice are essential steps in making informed decisions about neutral conductor sizing. Also remember that voltage drop can occur when the neutral conductor is undersized, leading to inefficient operation of electrical equipment. Overheating of the neutral conductor can lead to insulation damage and fire hazards. Harmonic currents generated by electronic devices can significantly increase the current in the neutral conductor. Multi-core branch circuits share a common neutral conductor, making accurate load calculations crucial. Commercial buildings often have complex loads and potential imbalances, requiring careful neutral conductor sizing. Dwelling units have specific NEC rules for calculating neutral loads. Undersized neutral conductors can cause voltage drop and equipment malfunction. The National Electrical Code provides guidelines and tables for calculating feeder and service loads. The 125% demand factor is primarily applied to phase conductors, not neutral conductors. The neutral conductor carries the unbalanced current between phases in a three-phase system. The neutral conductor is sized based on the actual load it is expected to carry. Continuous load is a load where the maximum current is expected to continue for 3 hours or more. The 125% demand factor accounts for continuous loading on phase conductors.